Welcome again in this video. As you all know, we have already finished all the discussions about conduction, and now we're heading to the next of the heat transfer mechanisms, which is the convection. Now, when we talk about convection or convective heat transfer, we are referring to the mixing of fluids by bulk transport. Now, to visualize this convection, we can see here a representation of air, and the blue one is something like a cold air. It mixes well with this hot air coming from the ground. So this is by virtue of what we call the natural convection. And I will be digging much on detail for that term, but before that, let me just describe this figure. Now, this is a pipe carrying hot fluid. As you can see, this is the cross section of that pipe, and assuming that we've dissected that pipe, we can see that the fluid is coming out from this pipe. Now, this is a hot fluid, and imagine if you have something like an ice here, that ice will simply melt, and then as you can see here, you will be having this water. And then when this water has already been melted, or it becomes liquid water, the transport of this the hotter region going to this cold region would be that it's not just conduction but also convection. Before, we used to solve problems involving conduction in pipes where we would always add something like neglect the heats of conduction. Well, simply because, neglect the heat of convection. That is because convection plays a vital role in differences in bulk transport of fluids. And now, since we're dealing with convection, we will not be neglecting those things now. Okay, but before we solve for that, let's just provide some information regarding convective heat transfer. Now, there are just two general types of convection. The first one is the natural convection. So this natural convection occurs in a way that there's a natural density difference arising from temperature gradient. And of course, since we have this kind of difference in temperature, it will cause this circulation. One good example is that when you're going outside and then you suddenly felt hot, that's basically because the air inside your house is a lot cooler than the air outside. So your body from the cooler region feels the warmth of the air the warmth of the air outside, and by convection you feel the air mixing with the air that surrounds you from the inside. Now, natural convection also occurs when we don't do anything just to mix the fluids that we have, and you'll understand that when we talk about forced convection. So forced convection is another type of convection in which we use mechanical means to drive the fluid. These mechanical means can be of fans, blowers, or pumps. For example, I want to I cooked, let's say, an instant noodles, and I wanted to immediately have it cooled. So instead of just waiting, so if I just waited and then let it cool in a natural way, that's natural convection. But if something like I place it in a water bath where it is a cold water, the temperature will decrease faster than it should be. So in that case, if it cools faster, you actually did something to have it cool faster, even though you didn't use something like fans or pump. The way you're actually defying the natural laws in convection, and in that way you're trying to do what we call the forced convection. And this is very essential in plants. As you can see, we're always trying to, for example, when we need to cool down immediately the equipment, we're trying to like add a cooler or a cooling system, and that's basically forced convection. And these two employ different ways of solving, and it's very important for us to understand this. But in general, as you can see the arrow here, we have the natural convection and forced convection. They just boil down to the same equation. That is a very simple equation Q, is equal to H, which is the what we call the heat transfer coefficient. Since before we're dealing with thermal conductivity for conduction, now we'll be calling something like a replacement for K, but not the actual replacement, but something that drives your, I mean, gives you the resistance. So this is what we call the H now, or the heat transfer coefficient. And and then this is the area of contact, and then we have TW minus TF. TW is based on our heat generation. TW was something like the temperature on the outside surface of the material, and that's the same thing for convection. TF is usually the fluid temperature, or the bulk temperature, or the average temperature. So if you have temperature, let's say a fluid flows like 35 degrees Celsius, so basically in that kind of problem, we're assuming that that's the average bulk temperature of water that's flowing. So it can equate to what we call the fluid temperature. And as a tip here, sometimes the fluid will not have really the same temperature readings, but since we're talking about the bulk temperature or the average, we need to take the average of the fluid temperature if we're not given just one temperature for that. So in that case, this convection, you might think, well, it's very easy simply because we only have like one formula to remember. Well, yes, that's true. That's just one formula, but I have highlighted H as you can see here. It's in a very bloody color, H, because H is actually a function of the velocity of the fluid, the temperature, the specific heat capacity, thermal conductivity, and etc. There's a lot like viscosities, the fluid properties, the density as well. So the most difficult part here that you'll be encountering in convection is not this equation but finding H. If the problem specifies H, you are very lucky to be solving a convective heat transfer where H is given. Usually this kind of problem occurs when you have a combined conduction and convection. So they are typically giving you the values of H. But if you're just solving for forced convection or natural convection, most of the time they will not, it is the thing that we need to find, and then just finding this will give us the answer already. So in that case, I'll just be giving you a grasp of what we'll be solving for now. So this is the mapping I just did for forced convection and natural convection. And I need to tell you that each of them has a different formula. They have distinct formula. So if I'll be counting this, we have 3, and then this one is I think 5, so 8, 9, 10, 11, 12, 13, 14, 15. So at least in this table I have 15 distinct formulas that I will be using for each case. And we're not still counting those that are under these others. It can be the annular, the triangular, the finned, all those things. And in cases where there's a boiling and condensation, I'm not yet including what we call the dropwise condensation and those things. So convection in summary is, I think, one of the most difficult that you'll be encountering in heat transfer mechanisms. It's a shame for all the unit operations in heat transfer. I think, and I personally think that convection is much harder than doing humidification, evaporation, crystallization. Convection exceeds them all. Okay, but of course, don't get intimidated because we'll only be dealing with those that are in red arrows. So you can see here this red triangles here. So in forced convection, we'll just be focusing on the laminar to turbulent pipes and cylinders. And for natural convection, what you have here is this vertical and horizontal cylinders, then denucleating film boiling, and then vertical and horizontal condensation. Now, um, I wanted you to I wanted you to take a good look at these pipes and various geometries. While for natural convection, you can see that various geometries and then boiling, condensation. Now, as what I've said before, forced convection is done through the use of mechanical means. That's why we would always be encountering problems in pipes since we're doing those mechanical means by using pumps and blowers. So that's a logical way of thinking that um, they should be delivered through pipes. Now there is the other like the various geometries where we'll be encountering annular ducts, external cylinders where there is a cross flow, then spherical surface, but these are much less. I mean, they are not more common than these pipes and cylinders. That's why I'm teaching just this forced convection. And now this one's natural convection. So there's this various geometry, and as you can see here, there's a vertical plane in cylinders, horizontal cylinders. Now, you would be asking, why do we still have some kind of cylinders here when you're not actually using pipes and pumps for natural convection? Well, the thing is, this can be storages. So if you're like storing water in a certain place, when when the temperature on the outside is a lot greater or lesser than your temperature, just if there's a temperature gradient. So for vertical planes and cylinders and horizontal cylinders, we're actually considering those fluids that are stored in a certain like storage tank. So even though they are cylinders, they must be having this convection still because if, even though the fact that they are not moving, it doesn't mean that they're not actually transporting these bulk elements. They actually do because they still have this temperature gradient we as compared with the outside temperature. And then the most practical application of this natural convection would of course be boiling and condensation. Since when there is a lot of heat transfer being generated in between these bulk molecules, what will happen is that there's a change of phase. And through that, we'll be seeing that there's this nucleate boiling, which is a kind of boiling. And then then there's this film boiling. Of course, since if it comes from a very high temperature and it is in a gaseous state, when it encounters a certain bulk element that is of colder temperature, condensation will happen, and condensation with respect to a surface can either be vertical or horizontal. So of course, the discussion about this boiling and condensation will be focused more after this discussion progresses. Okay, so this is just a warm up of that, and we'll be using this criterion to find our H. Okay, to find our heat transfer coefficient. So in the problem, you might be seeing a pipe that blah blah blah. So in that case, you'll be considering a forced convection, and then you'll be finding if it's transition, laminar, turbulent, and the same thing goes for natural convection. So it is also important for you to understand when it is forced and it is natural. And the idea is like, of course, when you have a pipe that is conducting a fluid or conveying a fluid, it is almost as if this is a forced convection. Since how can you actually deliver fluid when you don't have any mechanical means? So let's move on with a warm up. Now, before we solved anything from this table, which is a very tedious one, let's just first have some warm up. And this warm up is, I am calling this warm up because this is not actually the thing that makes convection difficult. This is actually very easy. Now, I wanted you to just remember your conduction. I've drawn something like this figure. And in your conduction, remember, disregard this red and blue here portion. This is actually not a flag, okay? Now, before in conduction, we used to describe the flow of it through this series of slabs. And through that, we need to find Q by using this formula. And we do have something like 3 slabs here, and of course, 3 resistances, so R1 to R3. Now, when we talk about convection, since we're already considering the effects of the fluid, we can somehow assume that there's another layer of a resistance here. But instead of you know, having a thickness, we're actually dealing with bulk molecules. So does this bulk molecule have some kind of thickness? So it doesn't have, since it's a fluid. So what we have here is that instead of representing that in terms of thickness, we're actually referring to that to them using this heat transfer coefficient, same as H. So if this is another resistance, so we'll be adding that to our equation, and the equation becomes something like this. We add some kind of resistance, and that is, we have, since we're not having this delta X, since they are not actually solid, so the fluid will be represented by 1 over HO. And HO is the outside heat transfer coefficient. And it makes sense for the inside, which is HI, the heat transfer coefficient on the inside. So this is dependent on the temperature and then the fluid that is inside and outside. So for example, the outside fluid is simply air, and the inside temperature would something like, for example, a hot oil. So we will be using um, the heat transfer coefficient for oil, and then the heat transfer coefficient for air for the outside. Now I want you to look at this A. That's actually the same area as these slabs. Now, why is that? So why are we using the same area? So since we're considering the heat transfer in like in this slab, so it is actually logical to use the area that is in contact with what is, that is in contact with the inside fluid. And the area that is in contact with the fluid is simply the area of this slab as well. So you'll be using the area in contact with the fluid. So if the fluid is actually at for example, the area is actually larger than this, larger than the 2, then you'll be using the area here for this slab, the area at this portion. Okay, so we're just referring this as A simply because the areas here are equal to each other. But if there's a certain difference, then they should be something like, if we set this as A1, A2, and A3, then A for HO should be A1, and then A for H3 should HI should be A3. Okay, so that's just how it goes for combined conduction and convection. It's not that difficult. Just remember that you just have to add this two portions. The convect we call this the convective heat effects. Of course, since they are obtained from the effects of convection. Now, I wanted to like factor out A here since they are just constant. So if we factor out, let me use just let me use this screen. So let's have a quick factoring for this. So that is the inside minus the outside, well, whichever is hotter. So we get 1 over A, and by factoring that we'll get 1 over HO plus let's just use this let's say resistance 1 and then resistance 2, and you know that that resistance is actually the value of this one, and then resistance 3, just to simplify this solution, so HI. Okay, and then since this is the reciprocal, I can actually put it at the numerator. So I have here A, and then the difference in temperature, and then this whole term here, we have 1 over HO plus all the resistances plus 1 over HI. Now, this whole term that we have here, this, not including the area, this, the one in the bracket, they can be represented as U. So that means I can write here U, and we call this the overall heat transfer coefficient. This overall heat transfer coefficient is equivalent to this 1 over HO, the reciprocal of this. So we have 1 over HO plus 1 over R1 plus 1 over R2 plus R3 plus 1 over HI, all its reciprocal. So this is another way of representing our general formula for the slabs. And if you're given already with U, then you can also use this equation. And if you would look closely, this looks kind of similar to this equation. It's just that this one is H because we're referring to a single convection for this. But in this case, since this is U, we're referring to a combined overall heat transfer coefficient for all the resistances brought by conduction and convection. So it will make a proper sense when I solve such kind of problem. But before that, let's try focusing on pipes. So the drawing here is something like this is like a corrugated circle, if you could see, but this is actually a fluid, and this one's also a fluid. So the pipe here is this gray area with another some kind of an insulation probably, or a reinforcement. Okay, so if we'll be solving just the conduction, we're just focusing at this point at the inner portion. So let me just like point it out. So the conduction will go something like that. But in with convection, it starts with from this fluid going out of this region. So in conduction, we're just focusing on these solid materials, but of course in convection, we're focusing not just on solids but also in gases or fluids. So the original equation would have been something like this. It's just the difference in temperature and then the log mean area, and then you notice there's this in the radius. Now, if we need to solve it with convection, we just need to add another resistance brought by the outside fluid and then the inside fluid. So just have to add it. And since we're much more versed in using the ln terms, not the logarithmic mean area, we can rewrite this. Actually, you can use this formula, but if you're like me, which prefers this, this formula where we only have ln of r sub 2 over r sub 1 over k, then this is the formula that you'll be using for such kind of problems. Okay, so this is what we call, we just have to add 2 pi l here, which is the 2 pi for the radius, and then the l here is the length of the pipe. That is actually constant for all the resistances and all these convective effects. Now I've redrawn this figure just to it's more pleasing at the eye, I guess now. So this is the inside concrete, then this is the fiberglass, and then outside, or the most outside portion, would be the gypsum board. And this is not the scale, since this one is very large compared to the first two. Now, it says here that the inside and outside convection coefficients are 2 and 7. So here we have HI, so that is the inside heat transfer coefficient. So we have here 2. So the unit would be, in English, British thermal unit per R, and then that is feet squared, and then degrees Fahrenheit. Now the next one would be HO, that is equal to 7. Okay, that has the same unit for this HI. Now, the outside temperature air is 20 degrees Fahrenheit. So we have here TO is equal to 20 degrees Fahrenheit. And then, of course, we have a side temperature, that is the inside. So we have TI equals to 72 degrees Fahrenheit. So the inside of this building is a lot hotter than the outside. So our formula before we used first lab would be this one. Okay, and let me just copy this so that it will be easier for us. Okay, so this is the formula for that, and we just need to substitute all the values and then obtain the value of Q. But I think the question is actually not Q, but the overall heat transfer coefficient for the wall. So in this problem, we are asked to find the heat transfer, overall heat transfer coefficient for the wall, the R value, and then the heat loss per unit area. So the first one is, we are tasked to find the value of our overall heat transfer coefficient, which is our U. So the capital U, remember, this is actually the reciprocal of all these stuff that we have here. Just I'm plugging out A from this equation. So that is, this one is equal to U and then area and then delta T. So we just need to find all the values of our 1 over HO, delta X 1 over K, and then take the reciprocal of that. So with that, U is simply equal to 1 divided by, let's just do this, 1 over HO plus delta X1 over K1 plus delta X2 K2 plus delta X3 K3, and then plus 1 over HI, and then we take the reciprocal of these. Now let us try to substitute all the values that we have here. So U, or the overall heat transfer coefficient, that is equal to 1 over 7, the outside is 7. So that is 7 British thermal unit. So the answer here is 247.9937. So the unit, so this answer is actually the answer for this one, but we need to take the reciprocal for this. So by the way, the unit here would be R feet squared degrees Fahrenheit per British thermal unit. And we need to take the reciprocal of this value that we will be able to get our overall heat transfer coefficient. So that is equal to 4.0324 times 10 to the negative 3. So we have British thermal unit per R, feet squared, and then degrees Fahrenheit. So this is our answer for this first question. So we have 4 to the negative 3 British thermal unit per hour, feet squared, degrees Fahrenheit for this lab. And if we're asked to find the R value, we just have to take the reciprocal of U. Simply because, since remember, this is the driving force. The driving force is actually the temperature, and then the resistance would simply be 1 over R, which is equal to U. So if this is equal to the driving force divided by the resistance, then it makes sense that resistance, or R, is equal to 1 over U. So 1 over U would be simply the answer, the value of this portion already, since we've already found the reciprocal for this, then therefore R is equal to this value. So R equals 247.9937. Then the reciprocal value would be R, feet squared, degrees Fahrenheit over British thermal unit. Now this is our R value, and that is the combined resistance for our slab. The heat loss per unit area, what we have here is this formula. And then basically, if we have Q and then U, we just have to take Q over A from this equation. So we have Q over A that is equal to UA. Q over A would be equal to U times delta T. So in this case, I'll be multiplying Q with delta T. Q over A is equal to U and times delta T, and that is equal to 4.0324 times 10 to the negative 3. You have British thermal unit per hour, feet squared, degrees Fahrenheit, and then you multiply this with the temperature gradient. So that is the inside and outside temperature. So we have 20 and 72. So we get here 72 degrees Fahrenheit minus 20 degrees Fahrenheit. So therefore, Q over A is equal to, so we cancel this Fahrenheit, and now we're left with BTU per hour per feet squared, and that makes sense since that is Q over A. So the answer would be equal to 0.20, 0.20997 British thermal unit per hour. That is the heat loss or heat gain. Let me just check if it's heat loss. That is the heat loss per unit area. So I forgot to write feet squared. So that is the heat loss per unit area. So British thermal unit per hour is our heat rate, and feet squared is our area. So that's it for the overall heat transfer coefficient, the R value, and the heat loss per unit area. So remember, the R value here is the sum of all these resistances. The reciprocal of our R value is our overall heat transfer coefficient, and that should be in British thermal unit per hour, feet squared, degrees Fahrenheit. The reciprocal unit would be for the resistances. Okay, so with that, let's answer the last problem for this, just to make you understand or warm you up before we start the forced convection. This is also a convection, but this is combined with conduction. That's why we're actually using some kind of the same pattern for our conduction. Now let's do this, number 2. This is actually located in your handout, the modules. So if you want to find them, then you just also solve it. But remember, I actually edited that number 3 because I don't know, I didn't add some fiberglass insulation, the thermal conductivity for this fiberglass insulation, since it's actually not stated in your Paris handbook. So I added it, it's 0.04 in SI units. So anyway, let's do this for number 2. And it says here that we have a steel tube. So the thermal conductivity for the steel tube is already given, and it has a wall thickness of 2 mm. So we can draw the figure first so that we get a good understanding of what's happening. So this is the steel tube, and the thickness is 2 mm, and the diameter is 3 cm. So let me just add here, the diameter is 3 centimeter, and then the thickness, so the thickness is the measurement of any portion here, just from the outside to the inside radius. So we get here thickness equal to 2 mm, and then the fluid flows on the inside of the tube, producing a convection coefficient. So this is the inside of the tube, and we have here HI that is equal to 1500 watts per meter squared. And make sure that you're checking the units of your HI should be in watts per meter squared. Yes, degrees Celsius. So remember, you should have that kind of units. Heat rate per area, and then temperature. Now the second fluid is from the outside. It flows across the outside of the tube. So it's like this behavior is often seen in heat exchanger, and the convection coefficient that is produced from the outside. So we have HO that is equal to 197 watts per meter square degrees Celsius. And of course, that degree Celsius can also be in terms of Kelvin. Okay. So, and now we have this inside temperature that is equal to 223 degrees Celsius. That makes sense that it is the hotter one, and the outside is the colder one. Actually, you will also always be encountering something like hot fluid on the inside, simply because it's like more practical to have the hotter fluid on the inside. Well, anyway, so that doesn't go well with cryogenics. But anyway, so let's proceed with the computation. So we can select where's that? We can select any formula from this, either this one or this one. But since I'm much more confident using this kind of formula, then I'll be using it. It's you're free to do so if you whichever you choose. So let's use it here. And I think we're good to go since this is already, I mean, all our given, the things that we need already given here. So with that, let's substitute all the values. And actually we need to calculate the heat loss by the tube per meter of length. So if we're talking about the tube per meter length, I need to have something like Q over L, just to have this, expression here. So that is Q over L, and then this one. Okay, and I just have to like remove L from here, and we're done. That is Q over L. Okay, and we will just have to substitute all these values from this equation. So Q over L is equal to Ti minus To. So we have 223 degrees Celsius minus 197 degree, not 197. That's minus 57. You don't have to convert this to Kelvin since you're subtracting. So anyway, so we have 2 pi, and then we divide this. So we'll be dividing this by, let's have some long line. So we'll be dividing this with 1 over RO HO. 1 over R sub O HO. So that means that I need to take the outer radius and then also the outside heat transfer coefficient. So our RO here, since this is 3 cm, that means that the diameter here is, the radius, or the outer radius, would be 1.5 centimeters. And of course, I need to convert this into MKS. So with that, that will be 1 over 1.5 over 100, then times our HO. HO would be 197, so we don't have to convert it anymore since it's already in MKS. And then we add the logarithmic difference of the radius of the radii. So we have 1.5 at R sub 2. Now for R sub 1, what we have here is simply R sub O minus the thickness. So we get R sub 1. So with that, R sub I is actually equal to 1.5 cm minus the thickness, that is 2 mm. So we just have to like divide this with 2. But since this is in mm, I need to divide this by 10 to get 18 centimeters. So the answer would be equal to 1.3. So the inner radius is 1.3 cm. So we have here 1.3. So I don't have to convert it to meters since this is logarithmic difference. So that is divided by K1. So K1 is the thermal conductivity of our steel tube, which is 46. Now, do I have to add something like ln of R sub 3 over R sub 2? So I don't have to do that since we actually don't have any insulation. It's just the steel pipe with some thickness. So we just have something like one resistance here. One resistance from conduction. So the next one will be plus 1 over r sub I. So we'll be using the inner diameter, inner radius, but I need to convert that um, to meters. So divided by 100 and then use the inside heat transfer coefficient, which is equal to 1500. Okay, so that is, I hope you understood my writing. It's really messy. So let's have some calculations here. You just have to like find QL here. Just use your calculator. So the answer for this problem is 2655.3013. So the unit would be watts per meter. Okay, so the unit should be always consistent with what you're solving. Okay, so this is how it is done for combined conduction and convection. Actually, this is actually not difficult. You just have to add this something like the resistance offered by convection. Now, if you're asked to find what is the total resistances, you just have to take all the resistances here. But the thing is, you have here the R sub 2 and R sub 1, and we usually take them out. I mean, yes, it's fine to use R here. Anyway, so you just have to take these values here, and that will be your R. And if you're asked to find U, then just find the reciprocal of that. I was about to mention this that you're not like allowed to simply use this since you have 2 pi L at the denominator. You actually have to like take it out from this expression. So this is the best choice that you have if you are finding R. But basically, when you want to find R for that, that most books do not actually require you to find that, since, well, it's much less common to determine that, because U is actually usually used for vessels, for storages, and yeah, for those materials that are lateral in orientation. So like this one, this is a building material, and it's easy to find U since we're not considering the area here. And in cases where we have something like this, the area actually varies from R1 to R2, and a U is usually referred to as something like it gives us a glimpse of the heating surface area. So if this is actually changing, then might as well rethink of using U for that. That's why some books are not actually using U for pipes. Instead, they're using this overall heat transfer coefficient for storages, for for plates, and you'll know that in unit operations we'll be using that since we have like a large vessels, horizontal or vertical, whatever the case. So I think that's all for now, and we'll be starting to solve. We'll go back here and we'll just take this a step by step, starting from the forced convection to laminar transition turbulent inside a pipe. Okay, so I wanted you to review your Reynolds number and momentum transfer, just to have it to make it easier for you to understand the lessons. Okay, so bye and thank you.